We're going to go ahead and look at inverse functions today. Inverse, an inverse undoes what the original function did. An inverse function only exists if the original function is one-to-one, which means it has to pass the vertical and horizontal line test. If your original function is written as f of x, we then go f with a little negative 1 exponent of x. Or if your original function is g of x, then we write its inverse as g with a little negative 1 and then of x. So to verify if a function and what you think its inverse are really inverses, you put one function into the other function. So you take the inverse, put it into the original, or you take the original and plug it into the inverse. If they actually simplify down to x, then you actually did find the inverse, or they are inverses. So let's go ahead and try to find the inverse of this. The original function just takes your input and adds 7. So your inverse should undo that. So it should take what you put in and just subtract 7. So let's go ahead and put one function into the other to see if it does simplify down to x. Your original function, f, says input plus 7. That's what it says, 7 plus your input. So I'm going to take what I think is my inverse and plug it in for my input. Now, I don't really need the parentheses because I'm adding. In a collect like terms, I get this. So yes, they are inverses since it just simplified down to a nice normal x. When we look here, g says input times 5. So your inverse more than likely should be just input divided by 5. It's got to undo that. So to go ahead and verify this, we need to take our original function g, which is 5 times input, and our input is what we think is our inverse, x over 5. So 5 times x divided by 5 is just x. So yes, these are inverses because it simplifies down to normal x. Now, when you get more than one operation going on, like this one here, where you're timesing by 3 and adding 2, it's a little bit harder to find your inverse just by looking at it. One way to do it is to switch your x and y values around and then solve the new equation for y. So remember, h of x is function notation, same thing as y. Bring this down. Now, to find your inverse, we got to switch our x and y. Now we solve it for y, so we can get rid of the 2 by subtracting 2 from both sides. Then we can go ahead and divide by 3, or multiply by 1/3. Now this would be our inverse. We had h of x here, so we go the inverse of h here. So now, to verify if this is correct, we want to take and plug in our inverse into our original. It's 3 times your input plus 2. 3 times your input, which we think is our inverse, plus 2. So 3 times your inverse, which is x minus 2 over 3. Notice timesing by 3, dividing by 3, they cancel, leaving us with an x minus 2 and an x plus 2, which does simplify down to x. So yes, they are inverses. If it does not simplify down to x, you either made a mistake or they are not inverses. Here, we are given a function. We're told that we're only dealing with x being greater than or equal to 0. So basically, we have a full parabola, but this x greater than or equal to 0 is limiting us to only half of a parabola. So if we make a t-chart and find that and plot that point or those points, we would get this red shape over here. It's just half of a parabola. Now, you could make yourself a t-chart. You know you're greater than 0, so I'm going to just try numbers greater than 0. You can take these numbers, square it, subtract 3. Plug in 1, square it, subtract 3. Plug in 2, square it, subtract 3. Plug in 3, square it, subtract 3. And plug in 4. If you plot those points, that's what gives us this red curve over here, which is our original function. And we can see from looking at this that our range, which is how far it goes up and down, is y is greater than or equal to -3. It starts at a height of -3 and it goes up forever. So y is greater than or equal to -3. Now we want to actually find its inverse. So remember, you got to switch x and y, solve it for y, and we really get plus or minus our square root of x plus 3. It's not really plus or minus. It's really just the positive root. Now, we switched x and y, so that means your original x and original y get switched. And so when you do that, this becomes y is greater than 0 when you switch x and y. So your y values of your inverse have to be greater than or equal to 0. So there's no negative in front, only the positive. By the way, the range of your original goes to the domain of your inverse. And you can see if we did that, it would be x greater than or equal to 3. I mean greater than or equal to -3. So now, if this is our original, your inverse, remember, has to undo it. So in other words, we have to put in -3, and it should give us out 0. If we plug in -2, it should then give us out the 1, because our inverse has to undo what our original was doing. And so you can see then that your ordered pairs are pretty much just flipped. Your x and y are switched, which makes sense because we actually switched your x and y up here to find your inverse. When you take these points and plot them, that gives you this purple shape right here, this purple curve. So the domain of your inverse starts at -3 and is greater than that. Your range starts at a height of 0 and goes up from there. So, numerically, looking at your table, how do you go from your function to your inverse? Well, you switch x and y. If you know the domain and range of the original, you can find the domain and range of your inverse by just switching the domain and range. What was the range of your original goes to the domain of your inverse. What was the domain of your original goes to the range of your inverse. Graphically speaking, how do we know what we have to do? Well, it's really a reflection over this y equals x line. If you take your original, reflect it over that y equals x line, you get your inverse. So graphically, you reflect over the y equals x line. So one more problem here to do to find your inverse. Remember, in finding inverses, we need to switch x and y. Remember, f of x is the same thing as y. So if we switch this to your x, these become both y, we would get this. Now we got to solve it for y. Right now you have y in the denominator and the numerator, but we don't like y in the bottom. So we're going to have to multiply both sides by y minus 2 to get rid of the dividing by 2 y minus 2 that it says. So if we do that, we get this. So now I'm going to just distribute through. I get this. Now I need to try to solve it for y. Right now I have a y on the right side and a y on the left side. So I'm going to choose to take the 4y to the other side. So subtract 4y to both sides. Now I'm trying to solve it for y. Since I'm trying to solve it for y, I don't want this part that doesn't have y's on that side. So I'm going to add a 2x to the other side. I'm not able to go ahead and combine these together because they're not like terms. Normally, if we just had a number times y, we would divide by that. But you will notice here that y is a common factor, so we could go ahead and pull out y. Now we have y multiplied by something, so to get y by itself, we have to divide by x minus 4. If we divide by x minus 4, we get this. Since we started out with function notation, we want to write it as function notation for our inverse.